Hello everyone and welcome to this brand new video. Today we are going to tackle backpropagation. And when I say tackle, I mean that I want you to know backpropagation so well that you can go ahead and implement a neural network from scratch without the need of using anybody else's code. This is for knowledge purposes, but also so that you can go ahead and implement maybe your own versions of neural networks with slightly different architectures or even massively different architectures. So before we dive into this video, I'd like to keep you up to date with the requirements. So things that you need to know is linear regression, how it works in a computer. And essentially I have two videos related to that. I have a video explaining the math behind a linear regression, and I have another one where I implement a linear regression on Python. So I'll leave the link for those videos in the description. The other thing that you should be familiar with is the feed-forward algorithm on a neural network. Now, I am not going to go through the particulars of how the feed-forward algorithm goes because I've already made several videos on that, which I'll leave the link in the description as well for those. Now, if you know linear regression and if you know feed-forward, then I am pretty sure that you should know matrix multiplication and addition, and you should also know partial differentiation and the chain rule. Now, I cannot stress enough how important the chain rule is for the backpropagation algorithm. It is essential to it. In fact, the backpropagation algorithm is the backpropagation algorithm because of the chain rule. So let's go ahead and set a quick example before we begin of a neural network and explain what the goal of the backpropagation algorithm is. So we have, let's say, a simple neural network here with one hidden layer. This is the input layer, right? This is the output layer, and this is the hidden layer. And this is a fully connected neural network or feed-forward neural network, right? So you should be familiar with this. Did I connect everything? No, I didn't. There you go. So you should be familiar with how these work. These are feed-forward neural networks or fully connected neural networks or linear neural networks. We have linear layers here, essentially. But what we want to accomplish with this is work through what is the backpropagation algorithm, what does it do for the neural network, and how can we use it to write a neural network from scratch. Okay, so imagine we have a set of inputs. Now our inputs are going to be most likely it's going to be a matrix, but for the sake of simplicity, let's say that we have a single set, a single input. Single input is going to be a vector, right? And this vector has x0, x1, and x2, which corresponds to these neurons here, right? It corresponds to these neurons here. These are the input neurons. Then we have the weights, which connect the input layer to the hidden layers and hidden layers to other hidden layers and the last hidden layer to the output layer. So these lines represent the weight, right? These are things that you should be familiar with already. Now, feed forward is about taking the input and computing an output for the neural network here. This last layer, or the output layer is the layer that we want to find. And essentially, this would tell us something about the input. Like, for example, we have inputs that tell us maybe what food we ate. And these neurons can represent different actions that we should take based on the food that we ate, right? So this could be go to sleep. This could be take a class. And the other one could be go on YouTube. Right? Great. So these are our recommendations. Now, the ideal thing here is that we have a set of inputs and we have a set of outputs that we expect for each of those inputs. And then we have some other set of inputs that we don't know the answer to, but would like our neural network to learn the patterns of the previous inputs or the previous sets, which we call the training sets, and apply it to the set of inputs that we don't know the answer to so that it can tell us new things that we didn't know. right? So great. So now that we have that into perspective, when we first create a neural network from scratch, the neural network is untrained. So it needs to be trained. It needs to learn the patterns of the inputs. Maybe it's an image and it needs to classify it. It needs to learn what are the things that are specific to the different images that make it be whatever classification it's supposed to be. Like, for example, a digit classifier, which is a very famous example of neural networks, right? The MNIST dataset. And it needs to learn that. How does it learn? Well, it uses the backpropagation algorithm, which is basically just calculus, chain rule. And that is what we're going to learn here. So the idea is when we first give it an input to I just created a neural network, or we just created a neural network, it's going to have an error here. It's going to have an error because when we randomly initialize a neural network, it doesn't know. It has no idea what the data set even is or what the pattern is. So at this point, it'll have errors. Now, the idea behind backpropagation is that you have an error, and this error at the last layer here, this error, pardon my handwriting, this error is caused by all of the parameters of the neural network, right? These weights are what compute this hidden layer, and then these weights are what compute the output layer. And we also have biases, right? So all of those parameters need to be tweaked so that we get the right output for the given input. So you can think of a neural network in a similar fashion that you do a linear regression. In a linear regression, we have a single input and we have a single output. But on a neural network, we have multiple inputs and we may have multiple outputs, right? And we have some hidden layers that do some processing between the input and the output. That is the essential difference between the linear regression and neural networks. Okay, great. So now that we have that, remember on linear regression, we have two parameters. We have the slope and the bias. And our goal is to change or tweak the slope and the bias so that for our given inputs, we get really, really close to our expected outputs. And that is done through iteration. So in neural networks, we do the exact same thing. Now, with a linear regression, we just have to compute the gradient of the cost function or the error function, right? We have to do the exact same thing for a neural network. It's essentially the same thing. So let's go ahead and define a cost function. Let's change back here to white and let's define a cost function. Now, for a cost function, I'd like to use this function here. Now, you should be familiar with what AL is because this is from our feed-forward neural network, right? AL is the output of the neural network, and Y is the expected output. This is the expected output. So this is part of our training set, right? This Y is part of our training set. And here we are finding the squared error, right? The mean squared error of the neural network. Now with this, we can now say, all right, can we find the derivative of this cost function with respect to all of the weights and all of the biases in the neural network? And the answer is yes, we can do it. How? Well, with the chain rule and with calculus. Great. So now that we know that, let's go ahead and see how we can go ahead and do that. So, by the way, let's go ahead and call these weights here, the weights that compute the last layer, we're going to call them WL. And this is a matrix, right? And we have here WL minus 1. And if we had any other layers before, it would be layer L minus 2, minus 3, etc., right? And we also have the biases, which we don't show here, but these are going to be BL and BL minus 1 as well. Great. So can we compute the gradient of the cost function, that is the partial derivative with respect to all the parameters? And the answer is yes. So let's go ahead and work through it. All right, so partial derivative of the cost, let's find it with respect to the weights on the Lth layer, meaning on the last layer. All right, so we just have to apply chain rule, and we say, all right, let's take the derivative of 1/2 quantity a to the al minus y squared, right? Let's go ahead and do that. And this is very simply 2 times 1/2 times al minus y. But remember, we're applying the chain rule. Now, y does not depend on wl, so the derivative of y with respect to wl is just 0. So we just have to take the derivative of a to the l, right? So times the derivative of al with respect to wl. All right, so since we know what al is, let's go ahead and define it in a form that will make this easier. So let's define a few intermediate functions. Let's go ahead here to the side, maybe to the side here. Let's define zl. I'll define zl as al, or actually let's define it for any general layer, right? So lowercase l, which could change, dotted with the weights at that layer. Actually, this would be al minus 1, right? Plus the bias at that layer. So this computes an intermediate value for a layer. Now we also have al, which is the output at one layer, and this is simply we pass an activation function to this intermediate value. So we should be familiar with this right now, right? We should be familiar with that. We also defined a cost function here. All right, and we don't have to really define the activation function to be able to work this out. So let's go ahead and not define it. So we have now the partial derivative of the lth activation with respect to the lth weights. Great, so let's go ahead and do that. And by the way, for the sake of showing how this differentiation works, we are going to assume that the weight and the activation and the bias is just a single number. That'll just make the math easier, but then later on we can adjust for that. All right, so let's go ahead and do that again. Well, first of all, these two cancel out, and we have al minus y times the derivative of al with respect to the weight. It's just going to be, let's just call it f prime of z to the l, right? So f prime is just this activation function. So let's put it this way: f prime of zl is the derivative of f of zl with respect to zl, right? So we're just making this clarification here just to ensure that we know what we're talking about here, right? So that's what f prime is. F prime is just the derivative of the function, the activation function with respect to the inner function, which is the z function. Great, so now we have that out of the way. Then we have that times the partial derivative of z to the l with respect to wl, which is what we're differentiating with respect to, right? Great, so now that we have that, let's look at our z function here. Our z function says that z to the capital L would be defined as a to the capital L minus 1 times w to the capital L plus b to the capital L. So it's easy to see from there that the derivative of z to the L with respect to wl is just al minus 1, right? Very simple. All right, we could also find the derivative with respect to b, but that's going to be the exact same thing, except that what are we saying? Instead of finding the derivative of z to the l with respect to the weight, we are finding it with respect to the bias, which is just going to be 1. So whatever this whole thing is going to be the same without this term, because instead of being a to the l minus 1, it's just going to be 1, right? So we can just say that the derivative of the cost with respect to the lth bias is going to be al minus y times f prime of zl. That's it. All right. But I sense that there is going to be a pattern here. Why? Because we are applying the chain rule over and over again. And now we're going to go into the other layer, into this layer. And we're going to find the derivative of the cost with respect to the nth minus 1 layer. All right. Let's go and find it manually, and then we'll try to see intuitively how we can go ahead and find that. So let's go ahead and do that. So cost derivative, partial derivative of the cost with respect to the L minus 1 weight. How do we start? Well, the cost, the derivative of the cost, we already took it, right? So it's AL minus Y, right? And then we have to derive A to the L with respect to WL to the minus 1. So just an application of the chain rule, right? Partial derivative of A to the L with respect to WL to the minus 1. Great. So let's go ahead and keep doing that. Let me even keep going here. All right. So we have A to the L minus Y times. All right. We still have to apply the chain rule here, right? So we have that A to the L is composed of two functions, right? The f function, which is the activation function, and the innermost function is the z function or the z function. So we have to apply the chain rule again here. All right, but this time we're deriving with respect to WL to the minus 1. Great. So now that we are there, let's go ahead and continue in this line. We have A to the L minus Y. And by the way, if you think I'm going too fast, go ahead and leave it in the comments so that I can go a little bit slower the next time. Also, go ahead and try to rewind and work through the steps that I am working on by yourself so that you can understand what's going on, right? So now that we have Z to the L, what is Z to the L? Z to the L, defined here, is just A to the L minus 1, capital L in that case, right? WL and BL. So we know that the only function there that depends on WL to the minus 1 is actually AL to the minus 1. And WL would just be a constant to that function. Therefore, our partial derivative of Z to the L with respect to WL to the minus 1 is just WL, right? Times the derivative of AL to the minus 1 with respect to WL to the minus 1. I hope that that is clear. Let's go ahead and do it once more. All right. AL minus Y times F prime Z to the L times WL times. All right. Let's see. What's the deal here? AL minus 1 is just the activation function, right? But we have to apply the chain rule, so we're going to do this. And this is going to be with respect to the inner function, right? But I'm not going to write it because we defined it here. We defined it here, right? That's what it is. And then we multiply a chain rule, right? Times the derivative of the inner function with respect to the variable, which is WL to the minus 1. And I've been saying WL to the minus 1 when in fact I mean the L minus 1 weights, right? The weights in the L minus 1 layer. All right, so let's continue on with the chain rule. And this is going to be very clear right now that ZL times WL times, just copying things over, right? Up until this point. But ZL to the minus 1 is just composed of WL to the minus 1 dotted with AL to the minus 2. And then the B is added, the constant, the derivative of a constant is just 0. So we're just staying with that. And again, the derivative of the cost with respect to the L minus 1B is going to be the same without this term, because the derivative of B to the L minus 1, it's just going to be 1. And this derivative here is going to be 0 when we're deriving with respect to B, right? Because these are just being added. This is a constant that's being added when we're deriving with respect to B to the L minus 1. All right, great. So now this is just AL minus y times f prime z to the L times WL times f prime z L minus 1, and that's it. We're done. All right, and we can sort of see a pattern here because, again, we are applying the chain rule. Therefore, we can go ahead and take advantage of this pattern to define the previous layers in terms of the error that is backpropagated from the layers that follow it. This is where the whole idea of backpropagation comes from. So let's go ahead and take a look here. If I have an error here, and I go back here, and I backpropagate this error, then this error depends on these weights that are here. And it also depends on how we computed the output of that layer, which depends on this function here, on this activation function. Now, look at the pattern that's happening here, because again, this is all the chain rule. We have these terms here. Let me use a different color so that it's clear to see. We have this right here, which we have also in the derivative of the cost with respect to BL. And this is the derivative of the cost with respect to WL, right? We have that term also in the derivative of the cost with respect to WL1 or BL1, right? L minus 1, I mean. And we are scaling that error by the weights, right? We are scaling that error by the weights. And we're also multiplying by the error that's introduced by the activation function. So that's pretty much all we need to do. All right, so let's see how can we take advantage of this pattern? Well, let's look at it. And let's define the error at the last layer. Let's call it delta, right? This is my delta, right? If we take our delta and we say our last delta, if we're using this particular cost function that we're using, the mean squared error, right? Our error is just going to be AL minus Y times F prime Z to the L, or the Lth Z. There we go. So if we define that as the error, then we can say, all right, well, the derivative of the cost with respect to the L is just going to be the error at that layer times the activation from the previous layer, right? The activation from the previous layer. And if we look at it, this matches what we have for the derivative of the cost with respect to WL, right? We have this error. And then we're multiplying or scaling by the previous layer, right? We have it right here. Look, we just have it there. The exact same thing, right? And then we can simply define the derivative of the cost with respect to the Lth bias is going to be just the error at that layer, right? And it matches what we have for the derivative of the cost with respect to BL. Just that, right? That's where we took it from. And that is going to be that error that we have at the last layer is introduced by all the previous layers. Therefore, that error is part of all the previous layers, right? Those errors are introduced by those layers. Therefore, they should be part of the error at that point. In fact, the error on all the previous layers, right? On all the previous layer depend on the error that we have at the last layer, because the last layer depends on the previous layers. I hope that's how we make it a little bit more intuitive, right? Okay, so now that we have that, can we then define the error at any given layer? Because once we know this, right? We know this. And this is always the case, right? For any cost with respect to any weight, the derivative is just going to be the error at that layer times the activation from the previous layer. So L to the minus 1. And the derivative of the cost with respect to the bias at any given layer is just going to be the error at that layer. That's always true. And we can see it with the pattern that we're following here. In fact, I encourage you to go ahead and take the derivative of the cost with respect to WL minus 2 and WB minus 2, WBL minus 2, so that you can see that this pattern is followed. And I hope that you can see it intuitively as well. All right, so if we define the error, all right, we know that we're going to have the error of the layer after there. But what is that error scaled by? Well, that error is actually scaled by the weight from the next layer. We can see it here. We can see it here, right? Because that weight is actually scaling the error. Every time we feed forward something up front, the weights are what are propagating the error. Therefore, that weight is guaranteed to make it that error is guaranteed to be part of the error from the previous layer, from where it originated, right? And then we multiply it times what? Let's actually put a parenthesis here, and you'll see why later on when we go into the linear algebra. And this is going to be times the error that the activation function introduces, right? If we have this, can we compute the error at L minus 1? And again, all you have to do to get this formula is follow the pattern. You can either do it intuitively, or you can follow the pattern while you derive. Those two ways are both fine. My goal is that if you can do it with the math, you can verify it with the math. You can also think of it intuitively. But let's go ahead and assume that you've already done this work and you accept that this is the case. So once we have that, can we compute the error at WL minus 1? And well, yes, we can, right? Well, if we follow this little formula here, then we can say WL to the minus 1, or actually delta L minus 1, or the error at the Lth minus 1 layer. This is going to be the error at the Lth layer times the weight at the Lth layer times the error at this current layer, L minus 1. Let's see. All right, but what is WL? W capital L. Sorry, I keep saying W. What is the error at the Lth layer? And we have that defined here. This is the only one that follows out of the pattern because it depends on which cost function we're using. But this is it, right? We have that L minus 1 equals. We have that delta L is this that we have right here, right? So it's AL minus Y times F prime ZL. All right, so this is this error right here, delta L. And then we multiplied by the weight here. I'm just copying this down, right? And then we multiply this by the error introduced by the activation function. Now, if we look at this, right, we can compute the cost, the derivative of the cost with respect to the WL minus 1 layer, which is just this multiplied, right? So we have this multiplied by this, we just subtract 1, so we have AL minus 2. And we can also compute the derivative of the cost, or the partial derivative of the cost with respect to BL minus 1, which is just this, right? And if we expand this, which I will not do, I hope you can see it that that's the case. If you expand it yourself, you can see that that is going to be the exact same thing that we have here, actually here. And you'll be able to see that it's also the same thing that we have here for the bias, right? Great. So now that we have that, we can go ahead and simply say, all right, this, the derivative of the cost, right, or Nabla cost, which is just the gradient of the cost, meaning the derivative of all the parameters that affect the cost, right? If we have that, we can find the the update equation for all the weights and biases of the neural network. And essentially, we can do the same thing that we would do in a linear regression, where once we have the how much this particular parameter affects the output, then we can change it so that we approach a minima of the cost, therefore minimizing. We approach a minimum of the cost, right? Which means getting the cost, the derivative of the cost, as close to zero as we can get it. And I hope that that is clear by you having watched the linear regression videos or even multi-regression videos that I've made in the past. If not, you should go ahead and do that. But once we have that, we can say that the update equation for any weight, the update equation, I keep doing the wrong thing here. Any weight should be updated by saying, all right, minus a small fraction, which we can call eta, of the derivative of the cost with respect to that weight. And then we can just do the same thing with the bias as well. We can update it very easily. Right? I hope you can see why this is the case from our previous videos on linear regression and multi-regression, if you want to see those as well. But these are going to be the equations that we're going to use to compute the weights in the Lth layer and the biases in the Lth layer, what they should go to in order to minimize the cost function of this neural network. Now, once we have that, we essentially have a neural network already. It's very easy to go from this to actually let's implement the backpropagation algorithm, meaning we can have a neural network built completely from scratch, and we can go ahead and compute the gradients. All right, so, and take a look at something here. The error at any given layer depends on the error on the subsequent layer. So this could give you a hint on how best this is implemented in code. Now I'll make another video where we go ahead and implement it from scratch using these equations here. And we can go ahead and see whether this works or not. All right, so now there is one last thing. So we have been just saying times. In reality, the error at any given layer is defined as the weights transposed times the error at the next layer. Actually, it's the weights at the next layer, right? And then all that Hadamard product, which is just element-wise multiplication of the error introduced by the activation function. Now, I can go ahead and show you why this is the correct operation, linear algebra, right? But what I encourage that you do with this is that you go ahead and see if this is the case and why this is the case. Because again, I don't want to do all the work for you, because if I do, you're just going to, maybe you won't do as much work as I would want you to actually learn this thing, and you won't be able to really learn it and be intuitive about it. So I'll give you this. This is the answer, right? But I want you to go ahead and try to see why this is the answer. And here's a little hint. We are propagating the error backwards, right? This is why this is L plus 1. And look at the weights. So the weights have a dimensionality, remember, right? The weights matrix have a dimensionality which depends on the number of input neurons and the number of output neurons. But now we are going the other way around. We are going from front to back, you could say. So therefore, look at this T right here, which means transpose the weights matrix. Go ahead and figure out why that is, which I've given you partial, a huge amount of the answer, too much. and see why we also have to use the Hadamard product here with the error introduced by the activation function. Now, with that being said, In the next few videos, we are going to go through the following, right? We're going to go through effective implementation of a neural network. I'm just going to say NN in Python. We are going to go ahead and we're going to use NumPy, right? We're going to use NumPy to implement a neural network using these equations from scratch. And I'll see you there. See ya.